As part of today's video, we are going to focus on what it means to save a signed integer and an unsigned integer, what all it means in terms of storage and how those numbers are stored. And in the next video, we will dive into how the floating point and double precision numbers are stored. So again, to go back and revisit our intention, we wanted to nail the 32 keywords of the C language. And well, if you want to follow along, then let's start our song and dance, which is, head to this URL here, which is github.com/in-pyjama/c-ninja-listings. Once you're there, this should be the repository that you see. And then we are interested in the code button here, right here. So once you're there, go ahead and click this arrow and you should see code spaces here. In my case, I already have a code space created. If you haven't already created, click this plus icon here and it'll create a code space for you. Now, code space is essentially a space wherein this repository will be cloned. All the utilities will be already installed so that you don't have to deal with the setup issues. Now that I have a code space already, what I'm going to do is click on the three dots here and then click on open in browser. Once I click here, in my case, I kind of already did it before recording the video. You will see that another tab opens up and you should see some window like so. Okay, let's go in the full screen mode. And we want to focus or revisit the file here. Let me open it up. Let me go to preview, close this. All right. So these were the C keywords that we were looking at and wanted to master. So let me just cross out the ones that we have already covered. So char or char, double, float, int. We mentioned that enums are somewhere related to int. We haven't discussed those yet, but let me underline it. Then long is something we have taken a look at, short, void, and return. Am I missing anything? Doesn't look like. 1, 2, 3, 4, 5, 6, 7, 8. So out of the 32 keywords, we have taken a look at 8 of those, and then 24 are remaining. Now, out of the 24, we are going to take a look at what signed and unsigned ints mean. Right. So, well, first off, signed and unsigned keywords are only related to char, int type of data types. And within int, then we mentioned that we have the keyword short and long. And then, long can be used as long. As a quick revision, this can be 2 to 4 bytes, 2 or 4 bytes, depending on the machine. Typically, it's 4. A short ensures that we get an integer that's worth 2 bytes. A long ensures that we at least get 4 bytes. Depending on the machine, it's either 4 or 8 bytes. And if we specify long, then we are sure that we'll get an integer worth, 8 bytes. All right. And now my claim is these two keywords right here only correspond to char and int, right? And first off, before, okay, let me just, okay. Let me just get my whiteboard. Very nice. So let's first take a look at how these numbers are stored, right? So we mentioned that if we are talking about a char, let's say a equals to 1, then there are essentially, first off, a character is 1 byte long, right? It's 1 byte long, which means there are 8 bits. And we mentioned the range is -128 to 127, right? And this can then be represented as 2 to the power 7 to 2 to the power 7 minus 1, right? That's the range. Now notice we have 8 bits, 0, 1, 2, 3, 4, 5, 6, 7 as the place value. Now the way this number 1 will get stored is this bit is set and rest of them are 0, right? And that's how we essentially count in binary. Now the interesting point is, to represent the number 127, we only need these 7 bits, right? 0 up to the 6th bit, which is 0th bit, 1st bit, 2nd, 3rd, 4th, 5th, 6th. The way the way the negative numbers are stored is that the 7th bit here has the place value of negative 2 to the 7. So if this bit is set, we would treat this place value as negative 128. Okay, and this gets interesting. So this is called the 2's complement way of storing a number. All right, let's try and see how a negative 1 would be stored, right? So let's say we have character b equals to -1. So question now is, how is -1 stored? So remember the rule of place value. So we have again 8 bits. And let me just quickly draw 8 bits, right? And we mentioned that the highest or the MSB position is treated as a negative number. So this happens to be the 7th bit. So 2 to the 7th is the place value, and that's treated as negative, right? And then this is 2 to the 6, 2 to the 5, 2 to the 4, and so on and so on, and 2 to the 0. Turns out if we have this bit as set, then we would have -128 as the place value of this position. And then if everyone else was also 1 here, then combined together they make 127. And when we add the place value, which is 2 minus 2 to the power, okay, let me represent this a little better. So this is treated as the sign field. So we treat that as -1 into 2 to the power 7. That is how this becomes -128, by the way, plus 2 to the 6 into 1, because this is a 1, plus 2 to the 5 into 1, so on and so forth. This is just general rule of place value when representing a binary number. And we are down to 2 to the 0 into 1 because of this, and every field is activated. My claim is, as you add all of these, this becomes 127. And then if you add both of these, it's a number -1. So this is how a -1 is represented. It's called, the storage mechanism is called 2's complement again, right? So look this up. And the idea of 2's complement is, if you let's say wanted to save the number -1 again, the way you're supposed to imagine is that you represent 1, then flip all the bits, so it becomes, and then you add 1 to it, right? So these are 4, these are 4. So this number here is representing -1 as noted here. So you take the positive part of the number, you flip all the bits, and then once you flipped all the bits, you add a 1 to it. So similarly, -2 would be represented as 4 zeros. This is 2. Then we flip all the bits and then add 1 to it. So we have 1 1 1 1, 1 1 1 0. So this is representing -2 in binary in 8-bit. Right? Okay, so this is how a character is stored. And then remember, we mentioned that a character is nothing but an int, which is 1 byte long. So similarly, if now maybe this is the time where I erase all of it. And now if we are considering an int, let's say an int a equals to -1, how would this be saved? Okay, now we have bytes. So each one of this is 1 byte, right? And remember, an int is essentially 4 bytes, right? And so there are 8 bits here, 8 bits here, 8 bits here, and 8 bits here. Oh, oops. Let me just bring that back. Okay. So a -1 then would be stored as this 31st bit here is represented as a negative value. So it's representing -1 into 2 to the 31. And then all of the other bits set together, 29 and so on and so forth to the power 0, will make up for 1 less than, so 1 less than 2 to the, well, actually 2 to the 30, well, let me just rephrase this. I made a mistake. So all of these together would be 1 less than 2 to the 31, right? And once you add this with -2 to the 31, you should get a -1 because it's 1 less than this number, right? So that's the idea. So if we store -1 like so, you will notice that all the bits are set. So again, this number is saved as -1 here. The negative numbers are saved as 2's complement in the 2's complement format. All right. So now the question is, what if you do not want to save a signed number? And at this point, I'll mention that signed int a equals to -1 is same as int a equals to -1, right? This statement and this statement are equivalent. When we do not mention the signedness of a number, it's assumed, like signedness of a integer number, it is assumed to be assigned. So this keyword here is just a explicit way of saying that, hey, I want int to be a signed representation, a 2's complement representation. And when we do not mention it, it's still a signed number. Now, if we were to say unsigned, okay, let me just get rid of this. Unsigned int a equals to 1, for example, then, well, essentially now, in case of an unsigned number, this 31st bit is treated as 2 to the power 31. Not as it was here, not like so. Not as a -2, not this, not this. It's treated as this. Now then what happens is the range of the integer will go from 0 to 2 to the 31 minus 1. Right? And similarly, in case we mentioned unsigned char, let's say b equals to 1. Oh, sorry. Equals to, this is not necessary. Let me get rid of that. Yeah, and this, then because of this keyword now, the 7th bit in case of character is treated as 2 to the power 7 and not 2 to -2 to the power 7. Now what will happen is an unsigned character then can go from 0 to 250, okay, can go from 0 to 255, which is 0 to 2 to the 7 minus 1. So that's the idea of signed and unsigned number. This keyword here essentially tells us whether the final MSB bit would be treated like a negative number, negative place value. The weightage of it would be treated as a negative number or not. And the way negative numbers are represented is using the 2's complement. And now with this set, with this as an example, or with this as the background, I have an interesting question for you that you can try and answer. So if we were to have character a equals to -1, we mentioned that this would be saved as all ones, right? All 8 bits would be saved as 1. My claim is that if I were to do unsigned here, okay, there should be space. So let's say I did SI the unsigned char or char b equals to -1. Now this sounds funny. We have a -1 here, but it's an unsigned character b. This will also be represented like so, but my claim is this is same as b equals to 255. And the reason to that has to do with this is treated as a -128 and this is treated as positive 128. Just again, based on how unsigned and signed variables are treated, right? Okay, hopefully this made sense to you. And now what we're going to do is quickly take a look at exactly precisely this example. And what you can do is, play around with this keyword, try to create your own disassembly and see, what happens. And all right, so let's go back to our workspace. Let's open up, just a moment. Let's open up the 𝗏.c here. So let me open up, okay, this was content from the last time. Let's get rid of that. Let's go ahead and save like -1 here. And then let's say, okay, I haven't tried this before, so let's see what comes up. Equals to -1 here. All right, we save it. I press Control and tilde. Then okay, get the terminal here. Make sure that you are within this directory, the keywords directory. And once you are there, hit make all. And you should see all of these commands executed. The result of that is, okay. The result of that is you will have the main.elf.lst file created, and that's where the fun stuff is. That's what we have been exploring. We don't need the terminal, get rid of it. All right. So as you can see here, well, we don't have the binary representation yet, right? But the interesting thing would be, okay, this is a this is a failed experiment. Okay, so let me see. All right, so you see that character A saved as -1, -1 here, loaded onto the stack again. And similarly, we have the unsigned B saved as a -1 here. Both the representations pretty much look the same, loading at this address. Now, I suppose what we'll need to do is launch. This is completely uncharted territory. So let me look up the command because, all right, so we are going to use the debug and the GDB, and let's make sure. Okay, let's make sure that our main.s is here. All right, we don't have the stack pointer set yet, and so if things work, they'll just work by pure magic. So all right, let me do make debug. Hopefully it works. We launched the QEMU session, then open up another terminal. Let me hide all of this, and let's see what shows up if I do make GDB. Very nice. Okay, and let's do next instruction. All right. Okay, I'll print the value of A, cannot access, right? I'm expecting that the current run of the current debug session runs into an error because the stack pointer is not set, and we are going to try and push stuff to stack pointer. This is tricky. Let's see, NI. All right, cannot access the memory, blah, blah, blah. So the problem here is that the stack pointer is set to something bad. Now we are going to do some experimentation, and I'll cut this part out if I fail at doing what I'm wanting to do, which is let's get rid of all of this. Let's get rid of terminal. I'm going to do something, which is before we jump, let's kind of load address sp, just randomly hex 8. So this is some black magic that I'm using. Let me go ahead and be like, okay, so this is the number where our program ends, right? So that's the number where our program ends. And what I'm going to do is just maybe randomly set this to 100. And if so, let me just explain what I did here. So as the CPU boots up, the first thing we do is say, hey, take the SP register and make it point to hex. Okay, there should be hex A1234100. So this should be 4. This should be 4. So 32 bits, right? So this is 4, this is 4, 32 bits, and this is a useful workable, like, a memory that you can work with. It's a memory that the CPU can access compared to the old X, FFFF, whatnot. This memory, the CPU wasn't able to access. All right, so I delete this. Let's see if this works. Hopefully it does. This is completely impromptu. I'll open up the terminals and then do make clean. Hopefully it works if I have the instruction right. Okay, we have to go to the keywords directory and then do a make clean, then do make all. It worked. All right, hopefully when I do make debug now, okay, make debug, get another terminal. Let me move the terminal window here just so that and let me hide the bottom one. And now I'll do make GTP. Very nice. Where is SP? SP is all zeros when I do an NI, which is next instruction. So we are essentially saying execute this instruction and stop. All right, that's what we are doing. Let me go ahead and execute that. Okay, SP became this. I have no idea how. Something bad. Oh, okay. You know what was the error? The error is I must, well, not must, I should have made it hex. So I'm going to quit. Let's first get rid of this. Okay, quit Q, yes. Where is my other terminal? Let's see, do I have it? Yes. Control A followed by S. Should have been Control AQ, but I pressed Control AC. That's all right. What I want to do quickly is go to this file and make this hex. Right now things would be okay. And so I do make clean, make all. Okay, everything looks good. Make debug. The QEMU is launched. We are in the debug mode. Let me go to bash on the terminal here and then do make GTB. All right, now if we see, this is okay. This is okay. What is going on? I have no idea. Okay, I need this. Right, so let's go. Yep, awesome. So now we have the right number here. Let me get rid of this. Let me type NI. Next instruction, please note this. Things are all right here. And then I'm going to do an NI again. Oh, okay, what is going on? I'm going to do an NI here. All right. Things look all right so far. Very nice. Now note, I'll do NI again. Okay, something happened. If I were to print A, it has a value of 0. Okay. Oh, I'm doing an NI, which is next instruction in hex, or rather, which is, this instruction right here. I zoomed out a little bit. So I do ni again. Oh, wait. Ni again. Right. And then I print a. Value of a is this. Print ni again. Okay. Print value of a. Value of a is 0, which is bizarre. Press ni again. Value of a. Ni again. Nice. So now if you notice, finally, the value of a is shown as 255. And recall a is -1, right? Why is it 255? Because the one byte that's represented here, everything's a 1. And when it is showing us here, it's showing it as an unsigned number, right? So all bits are set, the number would be 255. Okay, stay with me so far. Not all hope is lost. And what we are going to do is now going to print a, and it shows as an unsigned number. And now I'm going to do a step. Step means execute a C instruction all at once, which means it will execute the 2-3 instructions relating to the assignment of B. Again, what I mean here is if we go, so it would execute these 2 instructions at once. Let me go back here. Let's clear all of this. So step, right. If you see, B is also set to 255. Now, this getting set to 255 makes sense. My intention was to show you that this would be a -1. Turns out it is not. At least it's not shown that way. So let's see what I'm doing, if I'm doing anything incorrectly here. So I'll exit the current session and let's go back and see. Okay, let's go back and see if making it signed has any makes any difference. So fine, I'll bring up my good old terminal. I do Control A followed by X, then make all, right? Then make debug, hide this, then do a make GDB here. Very nice. Then I do a step. Oh, okay, wait. Then I do ni, and ni. Yeah, now let's do a step. Okay, very nice. Completely opposite of what I was wanting to prove. But I suppose the debugger is the one that is inferring that this is to be represented as an assigned number now. Okay, but again, my point that I originally made, which is this is enough to represent a signed number. That stays. The debugger is the one that is showing us the -1 based on the hint here. But that's all right. The signed keyword is not necessary. _A should suffice. You can try printing this on your local machine and it should show up as a -1. All right. What I was going to do is go back here, then do a step. And now you see at the point I was trying to make, which is B is represented as 255, A is represented as -1. In both cases, all the bits are set to 1. Right. So hopefully this convinces you about the signed and the unsigned keywords. And I understand that, the debugger kind of painted a different picture when I did not use the signed keyword. But my request is, please, on your local machine or in an online compiler where printf is available, try and print this, like the value of A and B, and see what comes up. All right, so I wanted to quickly demonstrate how you can write a program local. All right. Hey there. So I wanted to take a moment to demonstrate how you can go about doing the experiment of printing the values on your local machine. Hopefully you have GCC installed. If not, I'll just demonstrate it here and that should be good enough. So what we see on the screen is my terminal, and what I did was wrote a file main.c, and in that file we have content of this nature where, okay, just a moment. Right. So where if you see I have the char A equals -1, and then I have the unsigned char B equals -1. Claim was that this will be -1 and this will be 255. And even major claim was that the signed keyword is not required here. By default, char A means signed char A, right? And this is the special, some special syntax here, which we haven't discussed yet. But in the later videos, as we progress, all of this will make sense. What I'm trying to do here is to print on the screen the value of A and B as integers. Now, you don't have to go into the details of all of this yet, but just follow along that if I am, so at this point, I'll just go ahead and do GCC main.c. And once I do that, it gives me some warnings and this and that. That has to do with how my Mac works. But if I do ls, we see that there is, one more file here, which is a.out, which is the compiled binary, so to speak, right? We had the main.bin, all of that in our workspace, equivalent to that. Now to run this, all I have to do is to okay, only if, yes, /a.out. And once I run it, you will see that the value of A is printed as -1, whereas the value of B is printed as 255. Again, going back, this has to do with how the 7th bit in a byte is treated. In this case, this is treated as -128 as a negative number. And in this case, it is treated as 128, unsigned place value or a positive place value. And because of this, the summation of these bits here, which is 127, here, if you add 127, you get a -1. Here, if you add 127, you get 255. So that's the idea of the signed and the unsigned number demonstrated using the char. If we do the same thing for int, it would be pretty much the same, right? And well, can you guess what a -1, like, yeah, this is actually a good example or a good homework for you. So unsigned int c equals to -1. What would this be? So this is the highest possible value of a positive integer. That's what it is, a 4-byte worth of integer. All right, with this, I'll exit now and see you in the next one. Bye-bye.